This is lecture 9.1 through 9.3, and chapter 9 is on the different phases of matter and the attractive forces that are responsible for these different phases. We're going to start with the liquid-vapor equilibrium. We'll then, in doing so, we'll talk about boiling points and vapor pressure. We're then going to go on to phase diagrams, which is a two-dimensional graph illustrating the different phases of matter based on the combination of pressure and temperature. And then lastly, we're going to talk specifically about those attractive forces. Okay, let's go ahead and get started. And our first review question asks us to determine the heat of reaction for the decomposition of 1 mole of benzene to acetylene. And here's that balanced reaction. And we're asked to do so given the following thermochemical equations. If you're given multiple equations and asked something about an original equation, I think we know that this is about adding chemical equations together. Okay, so for those two new equations, let me call the first one 1 and the second one 2. And so I hope you recall how we begin. We begin by identifying, do we use each of these in the forward or the reverse direction? So for equation 1, I look to see what's part of my desired equation, and that would be the benzene, and it's on the left. I need it on the left, so equation 1 is used as written. For equation 2, I see acetylene on the left, but acetylene needs to be on the right, so equation 2 is inverted. Now let's look back at that benzene in equation 1 again, and I need one of them, not two, so I'm going to multiply equation 1 by 1/2, so I have one benzene. Let's look at equation 2 and the acetylene. There's two of them, but I need three of them, so I'm multiplying equation 2 by 3/2. Note the impact of multiplying either of these equations by some constant, meaning what's the impact on the enthalpy. Okay, I can actually now add these together and get my desired equation, and so I'm going to add half of the enthalpy from equation 1 to 3/2 of the enthalpy from equation 2, and by inverting equation 1 I already changed the sign. I might ask, does my answer make sense? And I really don't have anything to help me determine if this should be exothermic or endothermic, so I really don't have a lot of ideas as if this is correct or not. Sometimes we have good ideas if something is correct or not, sometimes not so much. But we still need to always ask, does our answer make sense? We're never going to catch those simple mistakes if we don't ask that question. Okay, now we're asked to use bond enthalpies to calculate the enthalpy of reaction for the combustion of hydrogen, and there's that balanced reaction. Okay, so we're using bond enthalpies, and we need to keep in mind that if you're breaking a bond, we're going to have a positive value. So the way these are illustrated would be for the breaking of bonds. For the formation of bonds, these become negative values. So again, breaking a chemical bond takes energy, so positive. Formation of a bond releases energy, so negative. Okay, so we have 4 OH bonds being formed. Because they're being formed, this is going to be a negative value. We have 2 HH bonds being broken, and 1 OO double bond being broken. Note how those are then positive values. So we need to just keep in mind and keep straight the positives and negatives ourselves by realizing forming bonds negative, breaking bonds positive. And I come up with negative 486 kilojoules. Does this answer make sense? Well, I definitely do expect a negative value, that energy is being released in a combustion reaction of any type. We're told the thermite reaction is an exothermic process that yields iron as a product, and here is the balanced chemical equation and the enthalpies of formation of the iron 3 oxide and the aluminum oxide, which is all we really need because the aluminum and iron are in their elemental state. Okay, and then we're asked to use enthalpies of formation to determine the heat release when 5 grams, that's not the quantities that we're going to get through the calculation, react with excess aluminum. So since 5 grams isn't the quantity that we're dealing with, we're going to use our units for that portion. But initially we're going to use our equation to calculate the enthalpy of the reaction. So again, the enthalpy of the reaction, delta H naught, is equal to the sum of the heats of formation in the products minus the sum of the heats of formation in the reactants, and you probably don't need to write that down all the time. The enthalpy formation in the products then will be the enthalpy formation of the aluminum oxide. Enthalpy formation of the reactants, we're looking at the enthalpy formation of the aluminum. Well, excuse me, that would be the iron 3 oxide. Looks like I have a typo here. Let me go ahead and get those two quantities. And when I put this on my calculator, I'm left with negative 851.5 kilojoules. Does that negative make sense? Well, we're told this is exothermic, so absolutely. We're not done because this is the enthalpy per the reaction based on the way that it's balanced. Now we're going to use our units for the second portion, which is to get the enthalpy for the 5 grams. Step 1, we're after an energy unit, so equals kilojoules. Step 2, we're starting with that 5 grams of the iron 3 oxide. And now on to step 3, let's get out of grams of iron 3 oxide. Here comes the big question. Can we go straight from grams of iron 3 oxide to kilojoules of energy? No. How do we get to kilojoules of energy? From moles. So first into moles of iron 3 oxide. Now that we're in moles of iron 3 oxide, we can go straight to kilojoules. Molar mass of iron 3 oxide is 159.7 grams per each mole. And we just calculated that we have negative 851.5 kilojoules per 1 mole of the iron 3 oxide. And I would remind you that in the balance equation, that might not be a 1. So double check that that was 1 mole of iron 3 oxide. And when I put this on my calculator, I come up with negative 26.7 kilojoules. Does this answer make sense? Well, the sign certainly does. And for just 5 grams, the magnitude seems appropriate as well. Okay, next we're told glucose reacts with oxygen to release carbon dioxide and water. We're given the enthalpy of formation for the glucose, the carbon dioxide, and that water, and then asked what mass of glucose must react to release 1,000 kilojoules of heat. Okay, well, this might be a good place for you to stop the presentation and come up with your own answer. Okay, first, what do we do? Well, we have two parts to the calculation. We're going to use our units to calculate the mass of the glucose associated with 1,000 kilojoules of energy. But before we do that, we're going to first calculate the enthalpy of the reaction. Again, enthalpy of reaction, delta H naught, is equal to the sum of the heats of formation in the products minus the sum of the heats of formation in the reactants. So we're looking at the heat of formation in the 6 carbon dioxides plus the heat of formation in the 6 waters, and then subtract the heat of formation of the 1 glucose. Let's go ahead and plug those values in. Put these numbers on our calculators. And I come up with negative 2,802 kilojoules based on the way the reaction is written. Does that answer make sense? And I'm going to say yes. This is a combustion reaction, so it's negative, and glucose is an energy storage molecule, so I'd expect it to be a reasonably large amount of energy. Okay, we're going to be using our units for the second portion of the calculation, and so step 1, we're after the mass of glucose. Step 2, we're looking for a number with a single unit to start the calculation with. And I hope you realize that's the 1,000 kilojoules of heat that's being liberated, and since it's being liberated, that's why we have a negative. On to step 3, out of kilojoules. Can I go straight from kilojoules to grams of glucose? No. Kilojoules takes us first to moles of glucose. Then from moles of glucose, using the molar mass, we can go to grams. For the numbers, that would be negative 2,802.5 kilojoules per each mole of glucose. And glucose has a molar mass of 180.0 grams per mole. And note, if you hadn't put in the negative with that 1,000 kilojoules, we'd come up with a negative mass. Would a negative mass make sense? I think it's obvious that would not make sense. It would have told us we'd made a mistake and to go look for what happened to our signs. And hopefully we would have found, oh, we just dropped the negative, not recognizing that by heat being released, that that's a negative 1,000 kilojoules. Simple mistakes are real easy to make, And a lot of them are easy to catch. But you have to ask that first question. Does my answer make sense? Okay, we're asked to use molar enthalpies of formation to determine the heat of reaction for the combustion of 1 mole of methanol. Okay, well, first we're going to calculate the enthalpy of the reaction. And we're looking at the sum of the enthalpies in the 2 carbon dioxides and the 4 waters, minus the enthalpy in the 2 methanols. Remember, oxygen would have an enthalpy of formation of 0, so we just omit it from our calculation. You can always write it in, but it's just going to be 0. We bring out those numbers and put them on my calculator. And I come up with negative 1452.8 kilojoules. That negative makes sense. Let's go on to the second part of the calculation. What's the second part? Well, we're asked for a single mole of methanol, so we're going to use our units for this. We're after an enthalpy, so an energy unit. We're starting with that 1 mole of methanol. And then that enthalpy of the reaction gives us the conversion factor from moles of methanol to kilojoules with negative 1452.8 kilojoules per 2 moles of methanol. Go back to the original reaction and see there's 2 methanols. So that's what I was saying earlier. Double check to make sure that coefficient is a 1, because it's not always a 1. And if you already were saying that is going to be the enthalpy of reaction divided by 2 because there's 2 methanols and we're asked about 1, well, your answer is correct, but this shows how we would get there using our units, which means how we get there reliably. Okay, which of the following statements are correct? The formation of a bond is an endothermic process. No, the breaking of a bond is endothermic. The formation is exothermic. The bond energy of a multiple bond is greater than that of a single bond. This is true. Bond energies of 2 different atoms are approximations. This actually is true. I think it means to say 2 different elements. And the bond energy required to break a bond is positive. This is true. You got to put energy in to break a bond. True or false, a reaction is expected to be exothermic if the bonds of the products are stronger than those of the reactants. Well, remember, we want the bigger numbers to be associated with the bonds that are formed. Hence, the bigger numbers should be associated with the products. And in a chemical reaction, the change in energies of the system and the surroundings are equal in magnitude but opposite in sign. This is absolutely true. Conservation of energy. And true or false, an expanding gas does work on the surrounding, thus W has a negative value, and this is true. Delta E equals Q plus W, where Q is heat and W is work. This is true. And if a reaction occurs at constant volume, then Q is equal to delta E, and this will be true because constant volume means we're not doing any work. So in that case, Q is equal to delta E. And if a reaction occurs at constant pressure, then work is equal to delta E, and this is no, because the constant pressure is what happened to your heat. So essentially, obviously, one way or another, we get the answer is no. Okay, on to new material, and we're going to be talking about different phases of matter and eventually the attractive forces between matter. Let's talk about the different phases of liquids and gases. There is an equilibrium that's going to occur between the liquid phase and the gaseous phase as long as we have a little bit of liquid there in the liquid phase. So imagine that I have an enclosed container. Just think of a bottle with a stopper in it. And I have a little bit of water in the bottom, and I put the stopper on, and I come back later and there's still water, then I have this equilibrium. Now, if I come back later and all the water is evaporated, then I don't have the equilibrium. It's all turned into the vapor. So I need to have at least a little bit in the liquid phase to have this equilibrium. Now, to talk about equilibrium, I would point out that that reversible arrow refers to dynamic equilibrium, which means that the forward reaction happens to be occurring at the same rate as the reverse reaction. It doesn't tell us about what the ratio of reactants and products are, it just tells us that the rates are equal. And so at equilibrium, we should have a constant amount of both. So a constant concentration in the liquid phase and a constant concentration in the vapor or gaseous phase. Now let me define vapor pressure, which is simply the pressure of the vapor exerted above its surface. So if you have a bottle of water, the vapor pressure of the water will be the pressure of the water right above the surface of that water. Now I would point out, let's go back to that bottle with that water, and as long as there is still some in the liquid phase and the rest has already gone into the gaseous phase, then it really didn't matter how big that container was. Now obviously a bigger container we're going to have more evaporate, but as long as we have just one drop of liquid, then essentially, and everything has vaporized, then we have this dynamic equilibrium, and the pressure of the vapor is not going to depend on the size of your container. Now, what about temperature? Is that going to have an impact on your pressure? Absolutely. As you increase temperature, you're going to increase your vapor pressure. No exceptions. Increase temperature, increase vapor pressure. Now that we understand vapor pressure and its relationship to temperature, let's talk about boiling points. First, the boiling point is a temperature, and it's the temperature at which the liquid would boil. So we might think of the normal boiling point of water is 100 degrees C. Well, I say normal because that would be at 1 atmosphere, which is normal conditions. I really should say at 1 atmosphere, water boils at 100 degrees C, because if I have a different external pressure, I'm going to have a different boiling point, a different boiling temperature. And so the boiling point of your liquid is going to depend on the external pressure, because the liquid boils when the vapor pressure becomes equal to the external pressure. Again, a liquid boils when its vapor pressure is equal to the external pressure. So you decrease external pressure, then your vapor pressure goes, then your boiling point goes down. You need less pressure to boil. Have greater external pressure, then your boiling point goes up, because you have to have a higher vapor pressure to essentially get to compete with the external pressure. This picture is trying to illustrate that this liquid is boiling when the vapor pressure, that would be the pressure of the vapor inside the bubbles, is equal to the external pressure. Now, I want to introduce you to the term critical temperature, and this is the temperature above which the liquid phase of a pure substance cannot exist. So above this temperature, you can't find your subject in the liquid phase. Now, it can be in the gaseous phase, and if all you did was increase temperature, you would go in the gaseous phase. If we would simply increase pressure, we might increase or go into the solid phase. But if we increase the temperature, we can never return to the liquid phase. Now, at the critical temperature, if we are at the pressure that keeps us in the liquid phase, so essentially the pressure to cause condensation of the liquid, then we have what's called critical pressure. So again, critical pressure is the pressure that must be applied to keep us in the liquid phase at the critical temperature. So critical pressure is based on keeping you at that liquid phase at that critical temperature. Now, it is worth noting that your critical pressure then must be equal to your vapor pressure at that critical temperature. So what's your vapor pressure at that critical temperature? That's going to be the same as your critical pressure. You may have heard the term supercritical fluid and wondered what it refers to. Now, if we take a substance and go above the critical temperature, remember, we can never be in the liquid phase. But if we are above the critical temperature and we have a pressure above the critical pressure, but not enough to go into the solid phase, then we enter what's called the supercritical fluid phase. Now, I'm going to give you a phase diagram in a minute, and then we'll talk more about supercritical fluids and critical temperature and critical pressure. Alright, let's go through some example problems first. True or false? Equilibrium has been established between a liquid and a vapor when there are equal quantities of liquid and vapor. False. True or false? Equilibrium has been established between a liquid and vapor when all the liquid has evaporated. No, you have to have some liquid left. When the liquid reaches its boiling point? No, at least not necessarily. When evaporation ceases and the concentration of liquids and vapor remain constant. That's correct, because you're going to first evaporate until you get to where the vapor is re-entering into the liquid phase at that same rate that the liquid is entering into the gaseous phase. So this would be true. And would it be true for the rate of the condensation equaling the rate of evaporation? And this is true. We have equilibrium. That means that the rate of the forward process and the reverse process are equal. True or false? The vapor pressure of a liquid depends on the temperature of the liquid. This is definitely true. The surface area of the liquid. This is not true. The volume of the liquid. This is also not true. The partial pressure of other gases over the liquid. The vapor pressure doesn't, but the boiling point would. So your vapor pressure doesn't depend on what other gases are present. And does it depend on both the temperature and the surface area? No, that surface area, not part of it. So vapor pressure depends on the temperature alone from these examples. Okay, true or false? The boiling point of a liquid is 373 kelvins, and that would be false. That might be the boiling point of water at 1 atmosphere. This is the temperature at which the liquid's vapor pressure equals 1 atmosphere. Well, if that's what your external atmosphere is, then yes, it would boil at that temperature. The liquid boils at a pressure at which the boiling point of a liquid is the pressure at which the liquid boils at 373. Again, no, for the same reason as A. The boiling point of a liquid is dependent upon the volume of the liquid. No. It's dependent upon the pressure above the liquid, and this would be yes. So here's our true answer here. The boiling point of a liquid depends on the external pressure, so the pressure above the liquid. Okay, methyl alcohol has a vapor pressure of 203 millimeters of mercury at 35 degrees C. If 5 grams is sealed in a 10-liter flask, what mass will remain in the liquid phase when equilibrium is established at 35 degrees C? Okay, well, let's see. We have a gas problem here, and for our gas problems, we used our units. Now, our primary equation, though, is we're after the mass that remains in the liquid phase, and the mass in the liquid phase is going to be that total mass minus the mass in the gaseous phase. The mass in the gaseous phase, again, from our gas law information, we're using our units. Step 1, we're after grams of methanol. Step 2, we throw out that big denominator line and then bring out the universal gas constant with moles in the numerator. I hope we can see we're going to get the grams from moles. Let me go ahead and bring out my volume in liters, my pressure in atmospheres, and my temperature in kelvins. That gives me moles of methanol. Now for moles of methanol, we go straight to grams of methanol, and the molar mass is 32.0 grams per each mole. And so the methanol in the gaseous phase would be 3.38 grams. We're going to subtract that from the total mass, the 5 grams, to get the mass that remained in the liquid phase at 1.62 grams. When answering these questions, make sure that there was enough original mass that there's enough to go fully into the gaseous phase. Okay, on to phase diagrams, which are a two-dimensional graph that essentially shows the different phases of matter based on a combination of the pressure and the temperature. So again, it shows you the different phases of matter based on a combination of the temperature and pressure. So again, we tend to have temperature running along the horizontal axis, pressure along the vertical axis, and note we have the solid, the liquid, and the vapor, and then these lines between them would be the point of equilibrium between them. So we can see where the solid's going to the liquid phase, and that's in equilibrium at D. And that the liquid is in equilibrium with the gaseous phase at that point B. Okay, so do note our phase diagram. And I hope that, and I want you to be able to not have colors or have labels and be able to tell just from the shape which is the solid, which is the liquid, which is the vapor, because they're all going to be very similar. Okay, now I want to introduce you to that point A on that phase diagram. Point A. This is what's called the triple point, and this is essentially the place where all three phases are in equilibrium. And of course, it's a combination of pressure and temperature. Now for water, we find our triple point at 0.01 degrees C, just barely above the freezing point of water under normal conditions, and at a very low pressure of 4.56 millimeters of mercury. Do you know that is very low pressure? Way less than 1% of normal atmospheric pressure. So at this very low temperature and a very low pressure, we have, actually what we have is the vapor pressure of our subject in the solid, liquid, and the gaseous phase are all essentially going to be equivalent. Keep that in mind. The vapor pressure, that's really part of the defining or driving force here. There's that picture again. And again, note A, our triple point, where all three of our phases come together. Okay, I imagine you've heard the term sublimation. Sublimation refers to the process where we go straight from the solid phase directly to the gaseous phase without passing through the liquid phase. So we go straight from a solid to a gas. Dry ice does this. Dry ice is solid carbon dioxide, and you'll never see liquid carbon dioxide because it goes straight from the solid to the gas. Iodine also does this. It'll go straight from the solid to the gas. Now let's talk a little bit about the melting point line that we saw on that phase diagram, and ultimately I want to talk about which way it leans. Sometimes it leans to the left, sometimes it leans to the right. We're going to find that it's going to lean in the direction where an increase in pressure ends up entering into the more dense phase. Now if we think about it, if you're squeezing something, it ultimately wants to take on the smallest volume possible, and the smallest volume possible would be the greater density. And so I hope it makes sense as you increase pressure that you're going to favor the physical state with the greater density. Now here are two phase diagrams. The one on the left, the liquid solid phase boundary leans to the right. The one on the right, it leans to the left. The one on the left, if we go just straight up, we see that right above it is the solid phase. In other words, increasing pressure here is favoring the solid phase, meaning solid must be your more dense subject, which by the way is way more common than the other way around. Again, it's way more common that the solid phase is the more dense phase, more dense than the liquid phase. Now, there is some instances where the liquid phase is more dense, and I'm going to ask you in a minute, give me an example of a liquid that's more dense in the liquid phase than the solid phase, because we all know of one. But do note, and on the right illustration, as you simply increase temperature, you're entering into the liquid phase. Again, you're entering the phase that's the more dense phase. So the one on the left illustrates the more dense phase was solid. The one on the right indicates the more dense phase was liquid. And now comes that question. Can you think of one example of a liquid that is more dense in the liquid phase than in the solid phase? Now, fortunately for all of us, water fits that description. Water is more dense in the solid phase, in the liquid phase than the solid phase. That's why solid water ice floats, because it's less dense than the water. Water happens to be at its most dense at 4 degrees C. Okay, so again, on the left we see the solid phase was the more dense phase. On the right we see the liquid phase was the more dense phase. Again, as you increase pressure, it's always going to favor the more dense phase. Okay, let's go through some examples. We're asked which of the following statements are correct. Gas, liquid, and solid phases of substances exist simultaneously at equilibrium at the critical pressure and temperature. False. That's describing what? The triple point. Above the critical pressure, only the solid phase of a pure substance can exist, and this is false. We need a this is not a very thorough question, because it's not talking about the temperature. You can have very high pressures and still be in the liquid phase. You just need to be under the critical temperature. And at very high pressures, we now know that we may favor the liquid or the solid phase, whichever is the more dense. And true or false, a liquid phase of a pure substance cannot exist above its critical temperature. That's pretty much the definition of critical temperature. The critical temperature and pressure cannot be produced simultaneously. This is false. We actually produce critical pressure at critical temperature so that we can essentially identify it. And above critical temperature and pressure, only the liquid phase of a substance exists. False. If you go above critical temperature, you can never be in the liquid phase. And all three phases exist at equilibrium at the triple point. This is true. And above its critical temperature and pressure, a substance becomes a supercritical fluid. And this is true, but we have to let me just clarify. If you just increased the temperature without increasing the pressure, you probably are going to enter into the gaseous phase. But if you increase the temperature and increase the pressure, then you're either going to be a supercritical fluid, or depending on your phase boundary between solid and liquid, you might enter into the solid phase. But under normal conditions of increasing both critical temperature and your temperature beyond critical temperature and your pressure beyond critical pressure, normally we are talking about a supercritical fluid. And true or false, a liquid boils when its vapor pressure equals the pressure above its surface. And I'm going to say true, but I'm going to put a little caveat in there, and I'm going to say as long as you don't have to worry about the pressure due to the depth of the liquid. The reason I put that caveat in there is because if we had a very deep liquid, then we have to take into account the pressure due to that liquid. I saw a presentation where a submarine, went down to some deep sea vents, and the robot arm on the submersible was reaching to grab a sample of water coming around the vents, and as the arm approached it, it melted. Well, the water wasn't boiling because of the tremendous pressures at that depth. So that's why I want to say that little caveat. It really is dependent on the pressure at the point of vaporization, but normally it's going to be based on the pressure above its surface. Okay, on the phase diagram below, which point corresponds to conditions where only the gas phase exists, and that would be point C. And on the phase diagram above, which point corresponds to conditions where both the solid and the liquid phase exists, and that would be point E. A is in the solid region, B is in the liquid, and C is in the gas. And now we're ready to talk about molecular, maybe I should say attractive forces, and we're mainly going to be spending our time talking about intermolecular forces. But first I want to talk about other attractive forces, and let's talk about ionic compounds. I know we're going to talk about these a little bit more later, but ionic compounds, the attraction of those oppositely charged ions is very strong, and so ionic compounds have very high melting points and very high boiling points. Same with metals. It takes a lot of energy to break apart those individual atoms because of the way that they are bound together. But when it comes to molecular compounds, to get these things to melt or boil, we simply need to to essentially overcome the intermolecular attractive forces. And most of our intermolecular attractive forces are quite weak. So ultimately your boiling and melting points are directly proportional to the attractive forces. If your melting points and boiling points are very high, then you have very strong attractive forces. If they're quite low, then you have very weak attractive forces. So just keep that in mind. Melting points and boiling points are an indication of the strengths of those attractive forces. Ionic compounds, very high. Molecular, much lower. And we have different types of molecular attractive forces, beginning with what are called dispersion forces, sometimes called London forces, but I always call them dispersion forces. And these are essentially the attractions between non-polar molecules. These dispersion forces are actually what's called an induced dipole. What they do is they induce a dipole. A dipole would be a polarity, and so they're inducing a polarity in adjacent molecules. So essentially, if your electrons go to one end of the molecule, so you have one end of your molecule is negative and the other end is positive, this has an influence on other molecules around it to do the same, to kind of bring their positives to line up with your negative and their negatives to line up with your positives. Here's a picture illustrating that. If in the atom on the or the molecule on the left, we induce this polarity, or we since you have this temporary polarity because the electrons are over on the left side of the molecule, well, it induces molecule on the right to essentially do the same. And I hope it makes sense that by having the left side negative on this molecule, that the other molecule wants to do the same thing. Why? Because now the side that's positive on the guy on the left is attracting the electrons from the guy on the right. So I hope indeed that we can see that these are induced. These are essentially an influence of this first molecule. Now let me point out that as you have larger and larger and larger atoms, you essentially can induce this polarity much more readily. So these dispersion forces become quite a bit stronger in larger atoms, and for that matter also in larger molecules, because larger molecules either have larger atoms or more atoms. The next attractive force is called dipole forces, which is essentially also called polar forces, and these are the polar attractions that result from having opposite poles. The negative pole of one molecule is attracting the positive pole of another, and vice versa. Here's an illustration of iodine chloride, and we can see that the negative chlorine is going to be attracting all the positive iodines in all of the adjacent molecules, and vice versa. The slightly positive iodine is going to be attracting all the slightly negative chlorines in the adjacent molecules. Positives attracting negatives and negatives attracting positives. So this is the nature of polar attractions, or dipoles. And these are going to be much stronger than dispersion forces. Dispersion forces are like a dipole, but they're fleeting. They only last a very small fraction of a moment. And so they're here and gone, here and gone, here and gone, whereas a dipole is a permanent polarity, and hence a much stronger attraction between polar molecules than in non-polar molecules, where those attractions are induced and hence fleeting, not very long-lasting at all. Okay, so again, dipoles much stronger than dispersion forces, and so our polar molecules are much stronger attracted to each other, and hence have much higher melting points and boiling points. Cooking water is a very polar molecule. Actually, it's an extremely polar molecule. We'll talk about this extremely polar molecule in a moment, but being very polar, it has very high melting points and very high boiling points. This is very fortunate for us. because if water was nonpolar, its melting point would be around, well, I'm going to say somewhere less than 40 below zero. 40 degrees C or 40 degrees F, they're both the same, just by coincidence. But essentially, can you imagine water only being in the liquid phase at temperatures below 40 below zero? I don't think we'd have life as we know it. So indeed, this is a very important thing. Okay, now I mentioned that water has extremely strong polar attractions, and this is because it can participate in what's called hydrogen bonding. Hydrogen bonding, again, these are all intermolecular attractions, so I'm not talking about a covalent bond to hydrogen. Hydrogen bonding results when we would have one of our top electronegative elements, actually we're talking about our small highly electronegative elements, so we're talking about nitrogen, oxygen, and fluorine. When one of these very electronegative elements is directly bound to hydrogen. At this point, these very highly electronegative elements are attracting electrons very strongly from that bond towards themselves, and really what we end up with is a very positive hydrogen, because remember, hydrogen, the hydrogen without its electron is a bare nucleus. So that hydrogen atom can be much more positive than just about any other atom because it doesn't have those electrons to essentially interfere. And so we have a very polar bond leading to a very polar molecule. So again, hydrogen bonding requires hydrogen directly bound to fluorine, oxygen, and nitrogen. Okay, we have an example question that asks which of the following exhibit hydrogen bonding. Okay, the guy on the left is ethylamine, also known as ethanamine. Ethylamine's an older name. But anyway, does that participate in hydrogen bonding? And the answer is yes, I have hydrogens directly attached to my nitrogen. What about the trimethylamine? No. Those hydrogens are on the carbon, they're not on the nitrogen. So we're not going to have the polarity in this fashion. And ammonia, yes. So I expect that ammonia and the ethylamine are going to have high melting points and high boiling points because of that high degree of attraction between them. Okay, which the following are true concerning dispersion forces? The strength of dispersion forces depends on the number of electrons in a molecule. In a bizarre way, this is true. And the reason it's true is because more electrons implies either bigger atoms, which means stronger dispersion forces, or more atoms, which also would mean greater dispersion forces. Dispersion forces are the primary attractive forces in metal-metal bonding. We haven't talked about metal-metal bonding, and no, dispersion forces aren't going to be part of their bonding. Dispersion forces involve the attraction between induced dipoles. This is true, almost a definition of that attractive force. Dispersion forces are the primary attractive force in molecular solids consisting of nonpolar molecules. This is true. Dispersion forces are the primary attractive force in nonpolar molecules. And dispersion forces exist in all molecular solids? And I haven't mentioned this yet, but the answer is yes. Dispersion forces do exist in, say, water, where we have hydrogen bonding. They're just not the dominant intermolecular attractive force. Okay, which is fine are true concerning hydrogen bonding. Water is less dense in the solid phase than the liquid phase due to hydrogen bonding, and this is true. When we enter the solid phase, the hydrogens line up with each other and take on just a little bit more volume. And with the volume going up, the density goes down. So that's why ice is a bit less dense than water, which is a very good thing. If ice was more dense than water, it would have sank to the bottom of the oceans, and essentially the oceans would have frozen from the bottom up and never melted again. So we're very fortunate about that. True or false, hydrogen bonds occur in molecules when NH, OH, and FH bonds. True. Hydrogen bonding in water results in lower than expected melting points. No, hydrogen bonding in water results in much greater melting points than expected. Remember, we would expect less than 40 degrees C. And it turns out to be 0 degrees C. Okay, the unusually high melting point of water, ammonia, and hydrogen fluoride are the result of hydrogen bonding. true. Hydrogen bonding is an unusual strong dipole force, and this is true. Hydrogen bonding is just an unusually strong dipole force. It's a polar molecule, but it's an extremely polar molecule because of those high electronegative elements being bound directly to hydrogen. Okay, what is the dominant intermolecular force in HF? Well, let's see. What is the dominant intermolecular force? Well, first, are they polar? And yes, HF is at least a polar molecule. Can it participate in extreme polarity, meaning hydrogen bonding? And it can do that as well. So hydrogen bonding is the dominant intermolecular attractive force in HF. What intermolecular forces are present in solid carbon dioxide? Well, first, is carbon dioxide polar or nonpolar? And carbon dioxide is nonpolar, which means dispersions. And it's a coincidence that's also induced dipoles. But learn the term dispersion. Okay, we're asked to arrange ammonia, methane, and phosphorus trihydride in order from lowest to highest boiling points. Well, let's see. Ammonia can participate in hydrogen bonding, so that's going to be high on the list. Methane is nonpolar, so it's going to be low on the list. And phosphorus trihydride is polar, but it can't participate in hydrogen bonding because phosphorus is not one of those elements. And so methane is lowest, phosphorus trihydride would be in the middle, with ammonia being greatest, again, because it can participate in hydrogen bonding. So phosphorus trihydride and ammonia are both polar, but we go to the extreme of polarity with ammonia because it can participate in hydrogen bonding. Okay, let's go over and practice some of the things that we've just learned. Water has an equilibrium vapor pressure of 71.9 nanometers of mercury. At 45 degrees C, 2.5 grams of water is sealed in a 5-liter flask. What mass of water will enter the gas phase? Okay, well, let's see, where do we begin? Well, first, what are we after? How much water will enter the gas phase? Okay, so how much water is going to go into the gaseous phase? And this is a gas problem, so we're using our units. Step 1, we're after grams of water. Since this is a gas law problem, for step 2, we begin with that big denominator line. And using the universal gas constant, we need what unit in the numerator? Moles. So we use the gas constant inverted so that moles is in the numerator. I hope we can see we're going to get grams for moles. Let's plug in our volume in liters, our pressure in atmospheres, and our temperature in kelvins. Again, that's going to give us moles of water. So out of moles of water and into grams of water, 18.0 grams per each mole. And when I put this all on my calculator, I come up with 0.326 grams of water. Seems kind of small, but that's not a very big pressure, is it? Less than 10% of atmospheric pressure, meaning 1 atmosphere of pressure. So I'm going to say, yeah, it seems reasonable. I would mention one thing, make sure there is that amount of water present. So let's say I only had 0.25 grams. Well, then 0.326 couldn't have entered, could it? So just always double check, make sure you had that mass to begin with. Okay, next, water has an equilibrium vapor pressure of 23.8 millimeters of mercury. At 25 degrees C, if 1 gram of water is sealed in a 20-liter flask, what mass will remain in the liquid phase when equilibrium is established? Okay, ultimately we're after the mass in the liquid phase, and that's going to be equal to the original mass minus the mass that goes into the gaseous phase. And now let's spend most of our time calculating the mass of the water that goes into the gaseous phase. This is a gas law problem, so step 1 equals grams of H2O, normal step 1. Step 2, a little bit different, where we start with the we start with the big denominator line, and then our universal gas constant with moles in the numerator. We're going to get the grams per moles. Very similar to what we did in the last problem. Let's plug in those values. And now that's moles of water, so one more conversion factor to get the grams of water. Again, it's 18.0 grams per each mole of water. And when I put this all on my calculator, I come up with 0.461 grams of water. So it didn't all evaporate. Okay, so the 1 gram minus the 0.461 grams gives 0.54 grams. And don't forget, throughout any of these practice problems, you can stop, come up with your own answer, and then continue with the presentation. Okay, on the phase diagram below, what point corresponds to conditions where solid, liquid, and gas phases all exist? Well, this would be at the point labeled D. And this is known as the triple point. And if a pure substance begins at point A, or the solid phase, and the pressure is reduced to point B, where we go into the gaseous phase, what process occurs? Well, what do we call it when you go straight from a solid to a gas? Sublimation. And now, which of the following substances has the highest melting point? Okay, well, first I'm going to look for ionic compounds because that would have the highest. Then I would look for hydrogen bonding because that would be next. Then polarity, that would be next. And then dispersion, which is at the very bottom. Okay, do I see any ionic compounds here? I do. Which of these is an ionic compound? And I would hope by this time that you can readily answer that question. If you can't, you really need to go back and read up on compounds. Ionic compounds, molecular compounds, and what's the difference between them. Okay, you may recall me saying we can tell if a compound is ionic because, or how, by determining if it has a metal in it. And the potassium in potassium chloride is a metal, which tells us this is ionic. And ionic compounds have much higher melting points and boiling points than molecular compounds, because in these instances we have to split apart the actual ions to get them to melt, which are very strongly attracted to each other. Okay, we're asked to arrange nitrogen, oxygen, helium, and chlorine in order from lowest to highest melting point. Well, all these are nonpolar, so they all consist of dispersion forces. Which is going to have the greatest dispersion forces? The bigger ones. So we're really just arranging these in terms of size. Helium smallest, then nitrogen, then oxygen, with chlorine being considerably larger. So again, for nonpolar molecules, the bigger ones are going to have the greater dispersion forces, and hence the highest melting points and boiling points. Okay, that concludes lecture 9.1 through 9.3, where we had our introduction to these different phases of matter. And talking about the different phases of matter, we talked about phase diagrams. And again, also talking about different phases of matter, we need to talk about the attractive forces, because the attractive forces really determine what phase are you going to be in. Okay, and that concludes this lecture.